Okay, let's get started today. So, a reminder that we do have a midterm coming up. I know still a little ways away, but it will be the week after spring break. So, there'll be the coding portion will be Wednesday, March 23rd in lab, and we'll include the material up through lists, so you will be expected to be able to use the list class from the standard template library. The paper version will be held Thursday, March 24th in class. It will be up through the material presented this coming Thursday, so it will include sets, maps, and associative maps. The coding portion, like last time, you'll be allowed to have a one-page cheat sheet front and back. Like last time, the paper version will be a closed note, closed book exam. Each of the two exams will include some material that gave you some difficulty last time. So the paper version will include a question on separate compilation and the also on bit shifting and bit operations. I'll go over that the Tuesday after we come back, so the Tuesday before the exam. I'll review separate compilation and bit shifting and bit operations, but those will be on it. And on the coding portion of the exam, it will include string, streams, and vectors. So specifically include some material on that, as well as things like classes and hash tables and lists, stuff that we've covered since the previous exam. Okay, so questions about that. So that's not this Thursday, but 2 weeks from Thursday. Yes, Judge.
Is Liz going to be on the coding portion?
Is what going to be?
List.
Yes, lists will be. So that's why it says up to lists. So up to and including lists. So lists will definitely, I've already got the test and there is a question involving lists on it. And if you look at the sample exams, there's a question from last semester that kind of gives you an idea of working with lists. Okay. And then second announcement is that there is no class on Thursday because I will not be in town, but I will be posting a video lecture from last year. So what I will be posting is a video lecture that goes over a brief introduction to Big O, using maps as associative arrays in the route intersection top coder problem. We are actually going to cover the colorful rabbits top coder problem in class today. So, as I say, there will be a lecture for you to view for March 10th, and I will hold you responsible for that lecture. In fact, you will probably be using maps as associative arrays. I'll probably mention it briefly today, but it'll be in more detail in the video lecture. Okay. And you'll notice the material from March 22nd, that will not be on the second midterm. That will be on the final. Okay. So today, we are going to be looking at, we're going to be finishing up, that's not really true. We're not finishing up sets and maps, so I won't say that. But say look at pitfalls. So that's one thing, looking at the pitfalls. Two, give you another, give you more practice. With sets and maps, so that's going to actually involve you doing the colorful rabbit program from Top Coder. And three, giving you a peek under the hood at how sets and maps are implemented. So far you've used them, but you actually haven't seen how they're implemented. Okay? So you've already seen from last time kind of how to use them, that they're essentially ordered. Actually, we'll go in maybe reverse order. We'll start with 3, giving you a peek under the hood. So I've already told you that sets and maps keep your items in some kind of order. So sets and maps keep the keys ordered. Okay, and find, insert, and delete can take log n, we'll say comparisons, where n equals the number of keys. So the question is, how do we manage that? Okay, with hash tables, what we did in order to get the really good performance was we randomized the keys. We applied a hash function to the key, and then based on what the hash value was, we went to that location in an array or vector, and we used a collision resolution strategy in case there was something already there. But sets and maps, we actually want to keep the keys ordered, so we can't randomize them. And what is done is it uses something called a tree. We'll actually consider trees. The last month of the course, we're actually going to be doing a lot with trees. But today is just kind of a quick look at what's going on. So the idea is going to be that the keys are organized conceptually. Let's say we have the keys 3, 20, 16, 15, 14, 12, 8, and 7. So those are the keys. That's the order they're presented to us. So what we do is we're going to create a structure that looks like an upside down tree. So think of a tree, it has its roots and it kind of goes up in branches. What we're going to do is start, and the first thing we do is we're going to put 3 into our so-called tree. Okay, so just like trees have branches, the trees we consider have branches too. They can have either a left branch or a right branch. Okay, think of a family tree maybe. So when 20 comes in, we look to see whether it is greater than 3 or less than 3, and we see that it's greater than 3, so we put it in what we call the right branch of the tree. Okay, and I'm actually going to have 1 here as well. So then 16 comes in, and we see that 16 is greater than 3, but it's less than 20, so we put it into the left branch for 20. Then 15 comes in. 15 is greater than 3. It is less than 20, so we go to the left. It's less than 16, and since 16 is what we currently call a leaf, so anytime something doesn't have a child, we say that it is a leaf. So right now 16 has no children, so we add 15 as the left child of 16. Okay? Then where do you think 14 is going to end up, based on what I've been telling you? To the left side of 15. That's correct. If I can get a cursor. Okay. Then 12 is going, and I'm not coming up with good ones. So let's come up, instead of using 12, let me next use 23. Okay, so 23 is greater than 3, greater than 20, so it goes over here. Okay, now I'm going to use 18 here. So 18 is greater than 3, less than 20, greater than 16, so it goes over here. So you can see what's happening is we're kind of getting an upside down tree. We call this element here the root. And we call the elements that have no children leaves. Okay. And you can see that this tree isn't actually well balanced. It's kind of right skewed, right? Because that initial value I put in 3, everything was going into what we call the right side of the tree. But if we insert, in general, our trees are going to come out, if the data is pretty random, it's usually going to come out fairly balanced. Okay? So we might then, 1 would end up over here. And if we have a completely balanced tree, and random trees, if you have random keys, the trees typically end up being pretty balanced, meaning that at each point, for each node, roughly half of the nodes are in the right half, and roughly half of the nodes are in the left half. That's a balanced tree. Okay. Well, remember what happens with binary search. If every time you divide something in half, okay, so with this node, if it has half the nodes and it's balanced, then roughly speaking, it will have n divided by 4 and n divided by 4 in each of its 2. So you can see what's happening is we're kind of always dividing by 2, and you can kind of hopefully see where this is going. Let's say we had 16 keys. Well, if that's the root, we'd expect that roughly 8 would be in each half. Okay. Then, so in each half, we have roughly 8. Then each of those would have roughly 4. And each of them would have roughly 2. And then each of them would have roughly 1, which would get us down to the leaf. And if you can see, we have, this is level 0, level 1, level 2, level 3, level 4. And that's the same as log 2 of 16, which is 4. So basically what we're doing with our trees is we're hoping that the keys are sufficiently random that we can roughly divide the keys in half, with half going into the left side of the tree and half going into the right side of the tree. And if each time we can further subdivide our sets in half, we end up with a relatively balanced tree whose depth is roughly log 2 of n. And therefore, we need roughly log n comparisons to find any key. Okay, because going back, okay, if we're looking for, say, 18, if we know that we kind of have the rule that all keys, say, greater than 3 are in the right subtree. And all keys, say, less than 3. So if we have 18 and we see it's greater than 3, we can eliminate the left subtree and presumably eliminate roughly half of our keys. Then when we go to 20 and find that 18 is less than 20, we eliminate both. We've now eliminated this part of the tree and this part of the tree, so hopefully we eliminated another quarter of the tree. And so we end up only having to make about log n comparisons if we're lucky. Now, it turns out that if the keys aren't random, we could end up with very bad imbalanced trees and we won't actually get such good performance. Kind of like with hash tables, if we're really unlucky with our hash function, we could end up having to look at far more than just one entry. So it turns out that there's also ways that you can rebalance trees as you're inserting keys so that the trees remain relatively balanced even if the keys aren't in random order. We'll be considering all that in another month. All I wanted to do here was give you kind of a peek underneath the hood so that you can see it's not magic. You can see kind of what the idea is that they're using for sets and maps. Here, we were assuming unique keys. Okay, multi-maps and multi-sets allow duplicates, in which case we would change the definition. We would say that one of the two trees, and we'd choose arbitrarily, could have keys, say, less than or equal to 3. So if this was a multi-set or a multi-map where the keys could be duplicated, now one of the two trees would be allowed to have keys that were equal to the root. So questions about that? Okay, we'll revisit this. This is what's called a binary tree, a binary search tree. That's called binary because it has each, we call each of these things a node, just like we've been calling them nodes in a list. Each node has at most 2 children, a left child and a right child. So we call it a binary tree. Okay. Like I said, you've probably at least seen family trees. Okay, so it's the same idea. Family trees have a root, some ancestor that you're traced back to who's kind of at the top of the tree, and then the tree comes down with the 2 sides of the family. That's not a binary tree because you can have multiple children, but it's the same idea. Okay. Okay, so first thing we wanted to do today. Second thing I want to do is talk about some of the pitfalls. There's one big pitfall that you can run into with sets and maps. So remember last time Dr. Planck was working with a roster of names, okay? And what he was doing was he was doing different things with counting first names or keeping collections of first names. So the last application we actually looked at last time was an application where we read in first name, last name pairs. Okay, so let's see. Here might be our names. And we kept a map where the key was the last name and the value was a set of first names. So for each last name, we wanted to keep track of all people who had that last name and what their first name was. Okay, so the program looked like this. Okay, so the map was actually a string and a pointer to a set of strings. You can see that FN set was typedefed as a set of strings. And we read each name into first name and last name. We found the last name. If the last name was not yet in our map, we added it by making a pair and creating a new first name set. Otherwise, we set first names to be whatever that existing set was. Either way, we either had first names equal to a new set or we had first names equal to an existing set. So when we came out of that if statement, first names pointed to something and we simply inserted that first name into the set. And we weren't worried about duplicate first names. If there were duplicate first names, they were discarded. And then at the end of the program, we iterate it through our map. So we iterate it through each last name. For each last name, we retrieved its set of first names. And then for each first name in that set, we printed it out. So a fairly simple program. But in doing it, he carefully avoided a pitfall that you could easily run into in your labs. And so we want you to avoid the pitfall. The pitfall is this. In maps, if your value field is an object, or let's say is going to say a collection, such as a set. Store the value as a pointer to the collection rather than as I'm just going to say, let's see, how do I want to say this? Store the value as a pointer to the collection. Let's see. Let me rewrite this. Okay, store the value as a heap allocated rather than a stack allocated object. So the pitfall is storing a collection of values as a stack allocated object. So heap allocated means you use new. Okay, so that's what he's doing here. When he says f names equals new fn set, he is using a heap allocated object. Remember, new allocates objects off of the heap. Okay, so he's specifically making sure that he is storing a pointer to this heap allocated object. That's what he's doing right here. It's a pointer to his heap allocated object. Okay, let's see what happens if you don't follow that little tip and instead you try to use a stack allocated object. Okay, so here he's changed the program very subtly so that now he's using a stack allocated object. He no longer has a pointer, it's a stack allocated object. Okay, So he's doing everything else about this program is identical to the last one. Okay. So he actually runs it, and he's running it with a very simple thing that has two names. And when he prints them out, he would expect to get the two names back, and instead he ends up with only a single name, which is the second person that he created. In fact, what do you notice here? What is the name that got printed? What's funny about that name? Look at the two names, and then look at that name. First of all, only one name got. You took the first name from one and the last name from the other, right? So that person that printed out wasn't even the name of either of those two people. So not only did we not print out both people, but the one person we printed out was an amalgamation of the two people we read in. So it's clearly a buggy program. So the question is, how did that happen? Okay, we used a stack allocated object for each of our sets, and I'm going to trace through the program and show you what happened. So we had two names. It was Adam Anderson and it was Andy Alleman. Okay, so the first CN statement reads Adam Anderson. Okay, and it tries to find Anderson, which is the last name. It fails, and so it inserts into make pair this LN, which is last name, and here he's created a set called first names. Okay, so over here we have F names, and we have LN. LN is currently Anderson. FN is currently Adam. Okay, F names is currently empty, which I'll denote as the empty set. Okay, so we first insert the pair Anderson and this empty set into last names. So last names now has the pair Anderson and an empty set. Okay, now we insert into first names FN. So into first names we insert Adam. Notice what did not happen. Nothing changed here. Why? Because when we insert it, F names right here, we made a copy. Okay? And F names is empty, so we ended up with an empty set here. And there's no connection between the set we created here and this set. So when we went down here and we inserted FN into F names, that had no effect on what we put into Anderson. So Anderson still has an empty set. Okay, so now we again read a first name and last name. So we've already read Adam Anderson. Now we read Andy and Alleman. Okay, we try to find Alleman, and we don't find it, so we make a pair with last name and first name. So what does F names contain? It contains Adam. So we end up inserting into here Alleman, Adam, which as you can see is not what we want because Adam is not the first name. But that's what we got because we made a copy of F names right here. Now we insert Andy into this set up here, but that's no good because it's the wrong set. Okay, and then we get down here and we print stuff out, and because we print out, we go through each last name, only Alleman has a first name. The reason Anderson doesn't print out in this for loop is it doesn't have any first names associated with it. So only Alleman prints out because only Alleman has a first name. As we can see, it got the wrong first name. And it was all caused because what we were creating here was a copy of a set that was slowly accumulating all the first names that we had ever seen. Basically, if you think about what first names is, it's equal a set of all the first names we have ever seen. Doesn't matter what the last name is, that's what that set is. It's a set of all the first names we have ever seen. So every time we create a new person and we create a copy of F names, we're actually just creating a copy of a set that has all the first names we have seen to this point in the program, which is completely wrong. Okay, what we wanted to do was create, when we first insert this, we create this last name, first name pair, what should be in the set that gets inserted here? What should be the set of first names when it's inserted right then? What was it earlier when it was up here? What was in it? Nothing. So what we really, when we are creating a new last name, initially what we want to add is something that has an empty set for first names. Okay, which is exactly not what is happening. We're giving it a set that has all the first names we've ever seen. Okay, so there is a solution to that problem. So the first crack at it is, instead of using F names, we can do the trick you used in 102, which is we can create an instance of fn set by calling the constructor. So by calling the constructor, we get an empty set. So that will at least fix the problem that we were assigning it before. We were assigning it the set of all first names we'd seen to date. Now we're ensuring we're only giving it an empty set. So that fixes that problem. Okay, but it's still not going to run properly. Okay, when he runs it, he gets no output whatsoever. So he fixed it, yet he got no output whatsoever. Okay, when he runs it right here, no output. Okay, so the problem is right here. when he sets f names to be equal to L_init second, he gets a copy. This copies the fn set to which that L_init second contains. So it's creating a copy. It's not assigning the actual set, it's creating a copy. So when you do the insert here, you're not modifying the original set, you're modifying the copy. Okay, the original set was an empty set. So the original set, so you modify, this modifies the copy. The original set is unchanged, and it remains empty. That's why nothing prints out here, because you never modify the original set. No matter how many times you go through the loop, you not once modify any of the original sets. And so all of the original sets remain empty. And when you reach your for loop here, nothing prints out. Do you have a question, Gavin? Or? Okay, so the problem here, what you're seeing is that these stack allocated objects are always getting copies created of them. And the problem is we keep modifying the copies rather than the original. And the problem is we have to modify the original. If we don't modify the original, nothing works. When we were back here with the heap allocated objects, it was all working properly. So back here, when we were using the heap allocated objects, everything worked properly because we were always pointing, when we did these assignments, we were always getting pointers to the original object. We never got copies. We always got pointers to the original object. So when we did our modification, we were modifying the original object. Okay, well, we can fix this copy problem too, but you're not going to like it because it involves something you haven't seen before. Okay, you'll notice that there is I've declared a new variable, and I've declared it with a reference in front of it. So what I'm doing now is saying that when I do the assignment of L_init second, it's saying give me a reference, which is really a pointer, to the original object. And C++ obliges us. So by putting an ampersand, by declaring a new variable called names, it's a totally new variable, and declaring it as a reference variable, it gives a reference to the original object, and now when I do my insert, it actually modifies the original object. Now you haven't seen reference variables before. This is not a reference parameter. This is called a reference variable. Okay? And we're not really going to discuss it much further in this class because it's pretty complicated to deal with. And when you're learning to deal with pointers, it doesn't really make sense to overload you with a different kind of pointer. This, in effect, is a different kind of pointer. But it does allow us to modify the original object rather than getting a copy. Okay? So the program works. If we run it now, it actually works properly. However, it turns out that the program is still inefficient because right down here, there's one more inefficiency. I'm going to let you take a minute or two and look at that code. And based on what I've told you, see if you can determine what inefficiency is in that circled code. So the code now works properly, but there's an inefficiency in the code that I've circled.
F names equals names.
Yep. So what I need to say is F in some sense. So you found that the problem was right here. This is also a copy operation. So there's nothing incorrect in this case, but it is copying whatever set is contained in second, and it's copying it. And that's inefficient. There's no reason to make that copy. Now, you would like to be able to say what you just said, which is you'd like to be able to say F names equals names. But you can't actually, okay? You're going to have to define F names as also a reference variable. So it's close, but you have to define a second reference variable. You can't even reuse them. So reference variables turn out to be constants by definition. So once you've declared and initialized them, you can't change them. So I have to, you notice that this is inside of a for loop. So every time through the for loop, it's getting initialized to a new value, and then it's going out of scope after each iteration of the for loop. That's why it works. Okay. This is just, so there's 3 bites at the apple here where you could go wrong. So basically, if you use, the moral here is if I use a stack allocated set as my value, I have 3 opportunities to go wrong. That's a lot of opportunities to get it wrong. Whereas if I just use a heap allocated set, I'm not going to go wrong. Okay, and this was a small program. Okay, if it was a bigger program, there would be just that many more opportunities for the mice to play while the cat's away. Okay, so the bottom line here is that if you're going to, in a lab, for example, hint, lab 7 is going to be that way, you're going to have to store in the value field another map or a set, make it a heap allocated value, and use a pointer to it. So, bottom line, use there. If you're going to have to use a set or a map in the value field, make it be a pointer. That is the pitfall to avoid. Okay? Questions about that? Okay, just a quick reminder that when you insert using either a set or a map that the return value, the first one, what's the iterator point to if the insert succeeds? The insert succeeds, what does this is the return value from insert. So you inserted a value, what does the iterator point to? The new, not the next element, the new element. Okay, points to the new element. If the insert succeeded. Okay, if the insert did not succeed, it points to the existing element if the insert failed. So if the insert failed, the only reason it fails is because that key already existed. Okay, so I'll say actually points to the new key, points to the existing key. And what does the bool indicate? Whether or not it succeeded. So that is true for a map as well. Okay, so that's a way that you can tell whether something succeeded or failed. Okay, so actually here was a very simple thing where he was reading in a set of names and he was simply trying to insert them into, so this program reads lines, inserts each line, into a set, and 3 for each line indicates if the insertion was successful. Which means if it didn't succeed, it was a duplicate. Okay, so all he's doing is doing the insert, getting the return value, which is this pair, and then he checks the return value and he looks at the dot second to see whether it succeeded or failed. And one thing is, in this case, it's a dot rather than an arrow. This is just something that you have to, with experience, you will determine when things are dots and when they're arrows, when they're pointers and when they're not. So in this case, the return value is a stack allocated object. It is not a heap allocated object. It's not a pointer. Yes, Ashley.
You say it will only fail if it already exists? But what
Yes.
if you were using a set of integers and you tried to push a string into it or something like that? Would it also fail? Or
The compiler would have complained already. It wouldn't have compiled. So the answer is yes if you could have ever gotten to that step, but the compiler would have already whined at you. It could fail too because you would run out of memory, but in that case you actually don't return to that part of the code. It turns out that it throws what's called an exception and you won't come back to that part of the code. So technically, I'm still correct. Other questions? Okay, time for a little bit more practice for you all. So, I want you to take a look at colorful rabbits. So if you want and you have your laptop, you can actually do it, but we're first going to think about the solution. So right now I just want you to read the problem statement. You can read it on your computer too. If not, you'll have to read it on my computer. And then we'll consider the problem, and then I'm going to have you program up the solution. Okay, so let's run through some examples. So here's our first example. So Cat Poochie, I'm going to say Poochie even though it's Pochi. I just like Poochie. So he's done an interview with 4 rabbits. So the first rabbit, the pink rabbit, said there's one other rabbit with the same color as me. This rabbit was interviewed and also said there's one other rabbit with the same color as me. And then 2 of the black rabbits were interviewed, and they said there were 2 other rabbits like me. So Cat Pochi is not guaranteed to interview every rabbit in the population. Okay? He's just recording responses for the rabbits he interviewed, and based on that, we need to calculate the minimum number of rabbits in the population. There may be more than that number of rabbits. Like there could have been a green rabbit, say a couple green rabbits that he never got to. So we may be understating the population, but this is the minimum number. So in this case, do we agree that the minimum number is 5? Does anyone not see that there must be at least 5 rabbits? Okay. So let's say that one rabbit is interviewed and says there's no other rabbits with the same color as me. So that's a minimum population of 1. It actually doesn't mean there's only 1 rabbit. Even though it says a poor lonely rabbit, there might be more rabbits than that in the population. It only means Cat Pochi interviewed 1. So here's the most interesting case. In this case, Cat Pochi interviewed, looks like 9 rabbits. Okay, so got a whole bunch of 2s. Okay, here's a whole bunch of 2s. Now, each rabbit was only interviewed once, so each of those 7 responses is a different rabbit. Okay, so the question is, how many different colored rabbits, what's the minimum number of different colored rabbits that we must have here? That is, how many, it's possible that each of the 7 rabbits that he or she interviewed is a different color. So it's possible that each of the 7 rabbits was a different color, right? And that there are 2 other rabbits with that same color. But we're interested in the minimum number of different colors. So what is the minimum number of, shall we say, tricolored rabbits?
6.
Pardon? Well, okay, let me try to, I'm still not asking this question right. How many distinct colors among those 7 rabbits? How many? What is the minimum? number of distinct colors? That's the question I'm trying to ask. We know the maximum number is 7. Okay, so one is 4. Another answer is 5 distinct colors. And another answer is 3. We're going to, and we have some people counting still. We're going to take a vote in a moment. You got a minute. So there are going to be 3 votes. There's going to be a minimum of 3 distinct colors, a minimum of 4, or a minimum of 5 based on these 7 responses. It may help to write down your rabbits just to, if you're having trouble, writing things down often helps. Try coloring the rabbits differently.
So, you said just because that one says 0 doesn't mean there isn't actually another rabbit of that color, correct?
No, the rabbit answered truthfully, so there is no other rabbit with that color. However, let's say that rabbit was green. There could be red rabbits in the population. So it was a little misleading to say a poor lonely rabbit. What it really meant is simply there's no other rabbit with that color.
So the rabbit know, but
The rabbits know. Yes, the rabbit knows how many other rabbits there are with that color. So up there, the pink rabbits each said 1 because there was one other pink rabbit, and the black rabbit said 2 because so they don't count themselves in this census.
so the value for that, you're not interviewing all the rabbits.
Right, he's not required to interview all the rabbits. Okay, time to vote. How many think that with these 7 responses that the minimum number of distinct colors is 3? Okay. How many think it's 4? And how many think it's 5? Okay. So let's take a look. Okay, so we have 7 2s, right? There's 7 2s up there. 1, 2, 3, 4, 5, 6, 7. Okay? These 3 could be red, right? Each of them, if interviewed, would say that there were 2 other red rabbits. These 3 could be blue, because each of them interviewed would say that there are 2 other blue rabbits. This one could be black. It would say that there's 2 other black rabbits. So in fact, the minimum number of distinct rabbit colors is 3.
But what about the 44?
And for
I'm sorry. We're not worried about that right now. I see what you all were thinking about. Okay. So you were thinking of the whole collection. I was just trying to say among the 2s. Sorry. I meant among the 2s. So for those of you who said 5 and were considering the whole collection, you are vindicated. But just for the 2s, there are 3 distinct. The minimum, there's got to be 3. So that means that for the rabbits that responded 2, there's a minimum of 9 rabbits in the population. So associated with the answers for 2, there is a minimum of 9 rabbits, because there are at least 3 distinct colors, and for each of those 3 distinct colors, there are 3 rabbits. Okay, now for the ones that respond, the one rabbit responded 44, so there must be 45 rabbits with that color. And for the one that responded 444, there must be 445 rabbits with that color, right? So overall, there's a minimum of 499 rabbits, which is the number that they came up with right there. Okay? So, from that, we want to come up with an algorithm for calculating the minimum number of rabbits. Okay? So the first thing that's probably worthwhile doing is, you don't have to, but it probably makes it easier if you increment each answer by 1, because that gives you the total number of rabbits with that color, right? If you increment each of the numbers in that vector by 1, that gives you the actual number of rabbits with that color, because the rabbit is saying, this is the number of other rabbits with this color. Then you have to add 1 for the rabbit itself. Does that make sense? Okay. Now, the next thing is figuring out for each response, like 3, is the minimum number of distinct colors you could have for that response. So we found that if there was 7 that responded 2, that there had to be 3 distinct colors. Okay? How did we get at that? Okay, in general, let's say that there was n responses. So let's say n rabbits said that there were x other rabbits. So n rabbits said there were x other rabbits with that color. What is the mathematical equation that gives us the minimum number of distinct colors? It's not actually n choose x. It is, okay, so it is n, it's not actually mod. It's n divided by x upper bound. Actually, it's n divided by x plus 1 upper bound, sorry. In this case, I said n rabbits said that there were x other rabbits with that color. So I have to add 1 to x. So in our case where it was 2, it was 7 divided by 2 plus 1. If you take the upper or ceiling on that, you get 3. Does that make sense? And then to get the minimum number of rabbits, you multiply by x plus 1. That gives you the number of rabbits, minimum number of rabbits that for that particular population. So that's the minimum number of rabbits responding with 2. Then you have to do it for every other, for 44 and 444. Okay. So then the question becomes, how is this related to maps and sets? Because today's lecture is all about maps and sets. Okay, so this is we're given, what we'll be given is actually a vector of ints that look like that. Okay. So I did say probably the first thing you want to do is add 1 to each element in the vector, but that's really immaterial here to our thing. How do maps figure into this? What do we have to keep track of? Yes. So if we read, so we start with a 2. What is the initial count for 2? 0, so we are going to set it to 1, right? Okay, now another 2 comes in. What's the most efficient way to find the existing count for 2? Well, what are the various ways we could do it? You have multiple ways that you could be storing this. Let's say it's at the end. We already have a number of pairs. We have 2 has occurred, say 5 times, 44 has occurred once, 444 has occurred once. How can we store those pairs? There's multiple ways we can store these pairs based on data structures you've had this semester. You could use a hash table. Okay. That the Kino lab. Okay. Yep. You could use a vector. Okay. Vector might be efficient. Maybe a map. No, we don't need a multi-map. Well, we're keeping for each. No, we could use a multi-map, but why do that? Just for each entry, we just, every time we see it, we increment the count by 1.
So you're saying that the keys would be...
The key is the number, like 2 or 444, and the value is the number of rabbits.
Then you have
That,
a huge data structure.
no, you don't. You have 3 entries here.
Okay.
Okay, so we could use a map, we could use a hash table, we could use a vector, we could use a list. That works too. Now, the most efficient structure, if you could use it, would be what? If you could use it, there's one data structure that is much more efficient than any of the other ones, if you could use it. Given that the numbers, if you had, well, there's one data structure. So we had hash tables, maps, lists, and vectors. We can actually organize this. There's a definite ranking of which is most efficient and which is least efficient. So let's actually put this up right now. So we have a vector, a list, a hash table, and a map. And in order to find something, we have a key like 2, and we have to find the key, and then we have to increment the count. What's the running time for find for each of these 4? Okay, I'm going to start asking. Let's see. Man in red. For a vector, what is the time for a find? Okay. Pardon? For a vector? Nope, it's not n. It is, okay, it is not log n for a vector. If you have a vector, okay, It's constant. It's just 1 because you go directly to it. All you'd have to say, if you had a vector like, say, count, you would just take whatever the rabbit said and increment it. If it was 2, it's direct. The vector is easily the most efficient. If you know the key, you just go straight to it. It's what we call order 1. We'll get to big O notation, but it takes 1 step. Of all the approaches, it is easily the most efficient. It's guaranteed that in 1 step you can find the right answer, the right entry. If you, okay, but, sorry, that's okay.
But in this problem, we don't have to find it.
Yes, you do, because you have these pairs, and you have to be able to efficiently find which count to increment. So if you used a vector, this will always give you a very quick access. Okay. A hash table also requires roughly 1, but not guaranteed, right? Because of collisions. Okay, so what is a map? I've told you several times how many steps are required to find something in a map. Log n. So that's not as efficient. And for a list, if it's unordered, how long is it going to take? N. So in fact, 2, 3, 4. The vector is the most efficient. The hash table is number 2. The map is number 3, and the list is number 4. Okay. Yes. Okay. So our first choice is a vector. So we should go and we should check to see, can we use a vector? Okay, so we have to go and look at the problem description to see whether a vector is the right call. And what we find is that it can be between 1 and 1,000,000. There could be up to 1,000,000 rabbits with the same color. That tends to make the vector not very feasible because it's going to be a very sparse vector. So while the vector looks appealing, we can't really use it because they intentionally did this to us too. They made it so that we couldn't easily use a vector. They just jacked up the size to a point where a vector was impractical. Okay, so a hash table is number 2. So you might justifiably say, why not use a hash table? Well, if the standard template library gave me a hash table, I would. But this is Topcoder. What is Topcoder all about? Where do I get all my points? Speed. And the standard template library, for reasons I don't understand, doesn't have a hash table. So I can either come up with a hash table from scratch, which is going to take me a lot of time and give me a crappy score, or we can go for option number 3, which is in the standard template library, is fast, or I mean, it's third best, but I'm going to get points for getting my answer in quickly. So it turns out I'm going to use a map. And just to quickly show you the solution to this problem, so here was my solution. So they give you that vector of replies. I created a map of rabbits. So the int was the the key is how many rabbits, other rabbits have that color, and the value is the number of rabbits telling me that. So all I did initially was go through my vector of rabbits, and I first incremented the number by 1, because if a rabbit said there were 2 other rabbits with that same color, I know there's 3 rabbits with that color, so I increment it by 1. I find it in the map. If that entry is not in the map, I add it to the map with a count of 1. Otherwise, I simply update the count. Then when I'm done, I use that formula that I showed you of n divided by x ceiling times x. I know it's x plus 1, but I already added 1 to it. So that's all I'm doing here is iterating through all my map entries, and I am dividing, doing integer division, and multiplying by first. So the first statement gives me n divided by x times x, but that doesn't give me the ceiling. Whoops. So the second statement is checking to see if there's any remainder. If there's a remainder, I have to add an extra n divided by x. So the second if is asking whether there's any remainder, and if the remainder is not equal to 0, I need to add an additional set of rabbits. And that's the rabbits I return. Okay, so this code will be in the video lecture, so you can take a look at it. It'll be at the end of the video lecture if you want to have a look at it. Okay, yes?
Isn't there a hash map in the standard library?
There may be now, but I think, okay, as of a couple years ago, it was considered an experimental addition to the standard template library. So let me check to see if it's now a permanent addition.
I've used it before, but
Okay.
I don't know how to use it.
So it's good. It's just that because it was experimental, it wasn't guaranteed to be. Depending on which implementation you use, it might or might not be there. Let me see. Okay, here's my guess. Even if it's still part of the standard, the problem is not every compiler implements the standard yet, so it's iffy. Maps are always there. Hash maps may or may not. That's my answer. Okay. So again, remember, no class Thursday, but there will be a video lecture, and make sure you take a look at that video lecture. And have a good spring break.